Hello and welcome. In the previous lesson, we learned how to call a C function from assembly code and vice versa. In this lesson, we shall learn about inlining the assembly instruction in C code text. The code snippet shown implements a program to blink the LED connected to the pin number 13 of Atmega 328 microcontroller through a 220 ohm resistor. The bit 0 of resistor DDR-B is set to 1 to configure the pin number 13 in output mode, and the bit 0 in the resistor port B is used to switch on and off the LED. Writing the bit 0 of port B with 1 switches on the LED, and writing 0 to it switches it off. And the function delay_ms provides the necessary delay. The same logic is implemented in assembly mixed C code. Note the initialization of DDR-B and port B is carried out using the assembly instruction. In embedded programming, on several occasions, implementing logic in assembly becomes more convenient and provides better control. For example, implementing sleep in assembly language is comparatively easier by use of sleep instruction than that in C. The delay function discussed in one of the lessons is implemented in assembly language. The usage of assembly provides better control to achieve relatively accurate delay, as the CPU cycle consumed per instruction is well known to the programmer. The statement shows the syntax of inline assembly code. The assembly instruction with input and output operand and clobber list is enclosed in parentheses preceded by the keyword ASM. The instruction inside the parenthesis has 4 parts separated by colon. The first part is the assembly instruction defined as a single string. Then the output operand list follows. The third part is the input operand list separated by comma. The output and input operands must be separated by comma, and it is mandatory. However, the output and input operand list may be empty. Finally, the clobber list follows. It is optional, including the colon. The clobber list includes registers which are not passed as operand but used in assembly code. The first part of the statement may contain more than one assembly instructions. For better readability, the assembly instructions are written in separate lines. Let's understand the format of inline assembly in more detail with an example. The code shows the implementation of integer division as inline assembly implementation. The function divide_int accepts 3 parameters: dividend, divisor, and quotient. The dividend and divisor are integer type, and quotient is an integer pointer. The quotient of division operation is passed back to the calling function in the integer pointer. The remainder is passed back as return value. And with reference to the parameter passing convention used by the compiler, the register pair R25 and R24 is used to pass the dividend. R23 and R22 is used for divisor, and R21 and R20 is used for quotient. And the remainder, that is the return value, is passed back using register pair R25 and R24 to the calling function. The flowchart describes the logic of the division using successive subtraction. The quotient is stored in the register Z as it is an integer pointer. The register pair R19 and R18 is assigned with the value 0, which stores the quotient of the division. The instructions CP and CPC compares dividend and the divisor. If the dividend is less than the divisor, the value of R19 and R18 is stored in the memory address pointed by the register Z, and the function returns. Else, the divisor is subtracted from the dividend and R19 and R18 is incremented. This continues until the dividend is greater than or equal to the divisor. In the implementation, we have all the four parts of the inline assembly code. The assembly instructions implement the described logic. Note, several assembly instructions are defined in the first part. The new line and the tab characters are included for the formatting of the assembly instructions in the disassembled file. The output and the input operand list define the relationship between the C operands and the registers. Note the string %2 in move W instruction. It refers to the third operand in the output and input operand list. Similarly, %0 and %1 refer to the first and second operands in the list. The string %A0 and %A1 in the instruction CP refers to the lower 8 bits of the first and second operands, respectively. And the letter B is used to refer the higher 8 bits of the operand. The operand dividend is read-write operand. This is described by the +R constraint before the operand. The plus sign is a modifier which tells the compiler the operand is read-write. The letter R is called constraint. Constraints define whether an operand may be a register and which kinds of register, whether the operand can be a memory reference and which kinds of address, whether the operand may be an immediate constant and which possible values it may have. The divisor and quotient are input operands and are read-only, hence no modifier. The assembler describes the constraints to be used with operands for each assembly instructions, and it must be used carefully. The C compiler checks the constraints used in the inline assembly used at the compile time. Finally, the clobber list follows. It is the optional part of the inline assembly statement and can be omitted with the colon. It is used to specify the registers used in the assembly code but not passed as operands. Notice the registers R19 and R18 are used in the code to keep track of the count of the successive subtractions, and the register pair is passed as the quotient of the division operation after copying the memory address pointed by the register G. The complete list of constraints and modifiers is provided in the link mentioned. It also provides the list of assembly instructions with the required constraints. You can find more information on the inline assembly in the provided link. Feel free to check out the link. The lesson described the basics of uses of inline assembly in C code. I hope it was informative. Thank you and happy coding.